This is Mr. Martin. These are video notes for Pre-Calculus Honors. We're looking at section 8.6 in this video with the counting principle. We're going to look at a number of examples to help us explain the concepts. And if at any time you feel like you want to try the examples on your own, feel free to pause the video and then restart it so you can check your answers. And then, as always, make sure that you write down your questions and ask them the next time you see me. So for my first example here, we want to determine in how many ways a computer can randomly generate two integers from 1 to 12 whose sum is 6. So we have to pick two numbers. So we're going to have our first number and we're going to have our second number. Now for our first number, we could have 1, 2, 3, 4, or 5. We can't pick any numbers higher than 5 because then the sum with the second number would be larger than 6, and we want to know numbers whose sum is 6. Okay, and then for my second number, we could also have the numbers 1 through 5, but I'm going to write these in a opposite order, so 5, 4, 3, 2, 1. So this is one way that I could have a sum of 6 if the first number is a 1 and the second number is a 5. Or the first number could be a 2 and the second one a 4, and so on. I could have a pair of 3s, first a 4 and then a 2, and then first a 5 and then a 1. So we see that there would be 5 ways that a computer could randomly generate two integers from 1 to 12 whose sum is 6. Alright, let's move on to example 2. Determine in how many ways a computer can randomly generate two distinct integers from 1 to 12 whose sum is 10. So now we're going to look at the numbers from 1 to 9. Okay, because anything larger than 9 would give us a sum larger than 10. Let's write these in the reverse order. 3, 2, and 1. So here's the first way, a 1 and then a 9, and we have all these different ways, but this way isn't going to work because we want distinct integers. So we're going to cross this one out, and now we can see that there would be 8 ways that a computer could randomly generate two distinct integers from 1 to 12 whose sum is 10. So moving on to the fundamental counting principle, we're going to let E sub 1 and E sub 2 be two events. For example, they could be flipping two coins. So event 1 could be flipping one coin, event 2 could be flipping a second coin. The first event, E1, can occur in M sub 1 different ways. After E sub 1 has occurred, E sub 2 can occur in M sub 2 different ways. Alright, so again, going back to my two coins, if I flip the first coin, there's two different ways that it could we could have an outcome. It could be heads or tails. That would be our M sub 1, and then our M sub 2 would be the same since we're just flipping a second coin. So the number of ways that two events can occur is M sub 1 times M sub 2. Okay, so keep in mind here, we're not really talking about probability yet. We're just looking at different possible outcomes. So for the next example, we're looking at a combination lock. We'll open when the right choice of three numbers from 1 to 30 inclusive is selected. How many different lock combinations are there? So we're going to have three numbers. So first number, second number, third number, and since there's 30 numbers, for the first number there's 30 possibilities, and then for the second number there would also be 30 because it doesn't say we can't use the same number twice, and then for the third number there would also be 30 possibilities, and our counting principle says that if we multiply these, the number of ways that two events can occur, in this case it's three events, is M1 times M2, so M1 times M sub 2 times M sub 3, or 27,000 different combinations. All right, moving on. Number 4, again, if you feel like you want to give any of these a shot, and then you can check your answer by restarting the video. So in a certain state, each automobile license plate consists of 2 letters followed by a 4-digit number. How many distinct license plate numbers can be formed? So we need spaces for 2 numbers, or 2 letters, and 4 numbers. So we've got letter, letter, and then 4 numbers. We know that there are 26 letters in the alphabet, so there's 26 choices for the first letter, 26 choices for the second letter, and there will be 10 digits for each of these numbers, and we're going to multiply these together to get the possible distinct license plates, and this should come out to 6,760,000 distinct license plates. Alright, so permutations, which we've talked a little bit about and you may have seen before also as well. A permutation of n different elements is an ordering of the elements such that one element is first, one element is second, one is third, and so on. So the key here is that the order matters. Alright, so sometimes we'll talk about lining people up. You know, the order in which you get lined up is important. Like example 5 here, in how many ways can 8 children line up in a row? So we've got 8 spots that we need to line children up in. So for the first spot, we have 8 choices of children that can go in that spot. For the second space, now we've used 1 for the first one, we can only have, there are 7 left for the second spot, 6 for the third, 5 for the fourth, for the fifth, 3 for the sixth, 2 for the seventh, and the last person gets the last spot. We're going to multiply these events together, and there should be 40,320 ways that we could line up these 8 children. Alright, so notice this suggests that if you want to order n elements, there are n factorial different ways to do that. So 8 times 7 all the way down to 1 is actually 8 factorial, which we can use if we are ordering n elements. Alright, moving on to number 6. 11 horses are running in a race. In how many different ways can these horses come in first, second, and third? So we've only got 3 places here. First, second, and third. And we've got 11 horses. So there are 11 possibilities for first place, times 10 possibilities left for second place, times 9 possibilities left for third place. That gives us 990 different outcomes for first, second, and third place. Alright, number 7. Student government has 15 members. In how many ways can a president and vice president be selected? This assumes that everyone is eligible to be president or vice president. So we're only picking 2, a president and a vice president. So there are 15 people to pick for the president, which would leave 14 people left for the vice president, or 210 outcomes for the election. Alright, so permutation, where order matters. Permutations of n elements take an r at a time. So we would say NPR, or the number of permutations of n elements taken r at a time, is n factorial over n minus r factorial. So this should say 6 and 7, I believe. Okay, so redo problem 6 using the permutation formula. So for number 6, we had 11 and we needed to choose to pick 3. So 11 permutations of 3. So that would be 11 factorial over 11 minus 3 factorial. So that's 11 factorial over 8 factorial, which is 11 times 10 times 9 times 8 factorial over 8 factorial. Those will cancel out. And again, we're left with 990 ways. And for number 7, we would have 15 that we're going to pick from, and we only need 2. So that's going to be 15 factorial over 15 minus 2 factorial. So we've got 15 factorial over 13 factorial, which simplifies to 15 times 14 times 13 factorial over 13 factorial. Those will cancel. We end up with 15 times 14, or again, 210 ways. So you'll notice this formula here, it's very similar to combinations, except we have to add one more element in the bottom when we get to combinations, like we used for binomial theorem. So here's our combinations where order does not matter of n elements taken r at a time. So not sure what's going on there. Hopefully it looks okay on your handout. But this should say n choose r, or we write it as n choose r or n choose r, just different notations, and it's equal to n factorial over r factorial times n minus r factorial. Okay, so this is when order does not matter. It doesn't matter the order that we pick the things, it just matters that we pick them. So for number 9 here, we have how many different ways can 2 letters be chosen from the letters A, B, C, D, E, F, and G. So we've got 7 letters, and we need to choose 2. So we've got 7 choose 2, or again we can write it as 7 choose 2. It's going to be 7 factorial over 2 factorial. Then we're going to subtract those. 7 minus 2 factorial. So we have 7 times 6 times 5 factorial over 2 times 1 times 5 factorial. This is my 5 factorial. Those are going to cancel. That's going to become a 3. And we get 21 ways. Alright, so for number 10, a standard poker hand consists of 5 cards dealt from a deck of 52. It doesn't matter the order that you get dealt the cards, it just matters which 5 cards that you have. How many different poker hands are possible? So we're going to have 52 choose 5. So we've got 52 factorial, so n factorial over r factorial, 5 factorial, then 52 minus 5 is 47 factorial. So we have 52 times 51 times 50 times 49 times 48 times 47 factorial over 5 times 4 times 3 times 2 times 1 times 47 factorial. Those will cancel out. Let's see, 5 times 2 is 10, so divide that by 10. We'll have 5, and we could probably do some other canceling too, but we'll just calculate the rest, and there would be 2,598,960 different hands. Alright, so that's going to be it for this video. If you had any questions, make sure you ask, and we'll see you in the next video.